Antonio and Federico.
Okay, so today we're gonna try to solve this problem. It is an incline. You have a block. I give you the mass. The mass is 2.5 kilograms, and there is a spring here at the end of the ramp. So the block is going to slide and compress this spring, and then we want to know how much is going to be the displacement of the spring. Okay? So we discussed about the potential energy before, right? Can anybody tell me what is your understanding about potential energy?
Stored energy.
Stored energy, right? And we have kinetic energy also, right? What would be kinetic energy?
Release energy.
And energy that's being used like in motion.
Motion, right? Kinetic means motion, so kinetic energy. And if I have, one example would be the marker. I have the marker here at a certain height. It has potential energy, right? What is the potential energy of this marker? What do you need to know to calculate the potential energy?
The height.
The height. What else?
The forces like gravity.
Acceleration of gravity. And what else?
The initial velocity.
Yeah, the initial velocity, but it's at zero. I'm leaving here. I'm that's the initial velocity.
What about the mass?
The mass, right? The mass. Okay.
I was gonna say-
Potential energy. Potential energy is EP is mgh, right? And remind me, what is kinetic energy? EK is equal to what? Do you guys remember the formula? One over two mv squared, right? V is the velocity. Okay? Now here, I'm just letting the block slide down, right? I'm not giving any velocity here. There's no initial velocity. So at this point, what would be the potential energy of this block?
Mass times the gravity.
Yeah, there is the height here, right? There is a height here. And the height from this point up to the spring is 4 meters. So I'm giving 4 meters. Now, there is a h prime here, a small height, that is related to the displacement. When the block hits the spring, it's going down up to a certain height. So this height here needs to be added to the potential energy, right? And this spring here, what is this spring? What are the example of potential energy we can have? Elastic, right? So the spring is going to have here some energy here stored, right? Related to the spring. Now, let's see if I can show this experiment here, what is called the Hooke's law. So I have here a spring, okay? One thing I want to show is that I have a spring. I want to put the mass here like 100 grams and maybe 200 grams. And you see that it's going up and down, right? Up and down. So it's a whole cycle, right? It's going up and down, up and down. It's a whole cycle. So from this moment, I start my clock. It goes up and comes down. That time of going up and coming down is called what?
Period.
Period, right? Remember, we had that with the circular motion, right? the time it starts until it comes to the same point, that is the period, right? So we see a period here. Now, if I remove, what do you notice? Do you notice anything?
Faster.
Faster, right? So it looks like the period here depends on the mass, okay? Now, this here, this is called pendulum, right? I have a string here, and you see that the pendulum is going up and come back. So the time that it goes and comes back is called
One period.
period also, right? Now, the period here is not going to depend on the mass. It's also not going to depend on where I let this go, okay? If it's here, it's going to be the same. The period here is going to depend on
The length.
the length of, you see that it's going much faster here, right? So this is something we're going to study next class, you know, the periods of these different things. But for today, before class started, I did one experiment. I was measuring, this is the position of the spring when there's no weight there. Then I put this hook here and I put different ways, and I measured the displacement of the spring. And then I put more, you see that it's going further down, right? So this displacement, I collect some data. Let's see if I have here in my computer. The displacement if I put this back close to the board. So if I have a table with the different masses and the displacement, I'm going to learn that it's going to be a straight line. So the straight line is related to a constant that depends on the spring. So the force is proportional to x, okay? So that's what we learned from doing this kind of experiment. Different springs, and we vary the masses. We're going to see that the force is proportional to the displacement. So here, we're going to have, as the spring gets compressed, right, we're going to have this restoring force, right, that is trying to push it back. When I pull the weight lower, right, I'm applying a force to the spring, but there is a restoring force from the spring trying to bring it to its position of equilibrium, right? Okay? Now, so this is the force. Now, the question is, what's going to be the energy stored on the spring? That energy stored on the spring is going to has to be equal to the potential energy. Remember, when we have a marker has potential energy and I let it go, it gets converted into kinetic energy, correct? So when the block comes here, it has converted the potential energy into kinetic energy, and is going to compress the spring up to a point that kinetic energy now has to be equal to this stored energy that the spring is going to have. Otherwise, you know, it would continue going, right? down, right? But there is the storing energy. The spring is going to hold it. So what is that potential energy? Now, if it's going to be the force, work is force times the distance, right? Now, if force depends on x, right? Force is not constant. If force is constant, right? This is force, and this here is distance, right? If I'm applying a constant force, I'm moving this thing up to a certain point, right? But the force is constant. So what is the work on a graph of force versus displacement? What is the work? What is the work? It's force times what?
Displacement.
Displacement, right? So in terms geometrically on the graph, what is F times X?
Fx.
Yeah, F is this value here, right? X is this value. What is F times X?
The area.
The area. Okay? You guys agree with me? So if the force were constant, the area would be just F times X. But here, on my experiment, I noticed that the force changes, right? Different mass that I put, I have different displacement. Different mass, different displacement. So the force increases. Well, if I want to know the work up to this value here, we know that the work is the area, right? So what is the area under this curve? It's going to be the area of a triangle, right? Well, the area of triangle is what related to the force?
Half.
Half.
Yeah.
Very good. Half. So W is going to be half F times X. But F is Kx. So the work here is going to be 1 over 2 Kx squared. So this is the energy stored on this spring. Okay? Yeah.
Just to get this right, it's not negative because it doesn't, the direction doesn't matter, right?
Yeah,
Because-
it doesn't matter here.
Because with force, there's a negative there.
Yeah, because the force is MA, right? Force is MA that is being applied there, but the spring is going opposite to it. That's why you have a negative here. Okay? Now let's go back to this problem here and try to solve it, right? Now we know that all this potential energy, so the way to write this is like this. Before the problem starts, we have potential energy plus the kinetic energy, that's beginning, right? It's going to be equal to the potential energy on point 2, this is point 1, this is point 2, plus the kinetic energy, plus the work on the spring, right? Okay? Now, if the problem says I have friction, right? If I have friction, then I'm going to have to add here a friction component of it, right? So it's the force of friction times the distance. But there is no friction on this problem. So potential energy is going to be what? mg h plus h prime, right? Because it's from here to here. The block stops at this point here, okay? And that is going to be equal, is there any potential energy here? No, it's 0, right? At this point, potential energy here is 0. Right? because that's the bottom, the lowest point it arrived. I'm considering potential energy from this point to here. Has any kinetic energy? No, the block compressed the spring and stopped. So there is no kinetic energy. So there is only the energy stored on the spring. And that is equal to 1 over 2 kx squared. And it's what the problem wants to calculate, right? It wants to calculate this displacement of the spring once the block hits the spring. Now, we have M. K is given. K is 300 newtons meters. Okay, that's K is given. I have H, that is 4 meters up to the point where the spring, it's not being compressed, right? And then I have this H line that I don't know, right? Let's figure out what is H line. Well, H line is right this here. It's right here. This is H line, and this here is my delta X, my X that I want to calculate. And this angle here is 40. So I can relate that trigonometrically, that the sine of theta is going to be H line divided by the delta X that I want to calculate. Okay? Is that good? So now let me write this equation here. I'm going to multiply this mg here. So I'm going to say mgh plus mg h line, but h line is x sine theta. Okay? And this is equal to 1 over 2 kx squared. So where is my variable? My variable is x and x squared. What kind of equation you guys think this is? Those are all going to be numbers, right? When I plug in m, g, h, m, g, these are all numbers that I have. Sine of theta is sine of 40. So I'm going to have here a coefficient, let's say c, plus, let's say here is going to be bx, and here this is another coefficient. I'm going to call this ax squared. So I'm going to have ax squared minus bx minus c equal to 0. What kind of equation is this?
Quadratic equation.
Quadratic equation. So you can find the value of x. Okay? So I'm not going to solve it. You guys need to plug in the numbers here. You calculate, and then next class you guys check the answer. Okay? You can check with each other. Yeah.
My question is, like, I get what you're doing, but then how do you derive, like, the potential?
Potential
Like, how did
energy?
you derive the whole equation?
Yeah. Well, the energy before needs to be equal to the energy afterwards, right?
But then
Conservation
now-
of energy.
And now this time you're including work, right?
Yeah, the potential energy has been converted into this work of that being stored on the spring.
Okay.
Okay? And there is no potential energy here at this point because this is the bottom. There is no kinetic energy there. So I have to I wrote down the general form. And then I start. There is any kinetic energy here? No. But if the problem had said the block has velocity of, let's say, 10 meters per second, right? Then on top of having potential energy, that is this here, is going to have also kinetic energy. So you need to add the kinetic energy. And what is kinetic energy? Is 1 over 2 mv squared.
So what you're doing is, so you're adding the potential energy from the block So it has to be equal to the potential energy of the spring.
on the spring, yeah.
Okay.
Basically, that's what it is, because this is 0, this is 0, this is 0, right? I'm just putting
But
here,
it-
just in case you find another problem that is giving you some velocity, some, you know, and then you need to consider that.
So the potential energy of the spring, are you considering since the point the block touches the spring or after it reaches its maximum?
Yeah, it's from the point of equilibrium of the spring without any.
Without nothing touching it?
Yeah, and then at the point that it stopped,
Oh, okay.
okay? It's like here, this spring I have here, there is no weight, right? And I put some weight, so I'm applying a force on the spring and that stops. So this is delta X.
Oh, okay, so it'll be.
It's
but-
just that here is for compression. I can do that too if I push the spring up, you know,
Yeah.
try to compress that.
And that'll be like, that's the displacement, right?
Yeah,
Yeah,
and
okay.
the force is calculated by this constant K that depends on the spring times the displacement.
I have a question.
Yeah.
The H 4 meters, is it from the block to the spring or from the block to the bottom?
It's from the block to the spring
Okay.
at equilibrium.
All right. And then the H prime is.
H prime is
it's
the
just the
displacement.
length of the spring,
Yeah.
the compression of the
It's-
spring.
A compression of the spring. So,
Oh, okay.
so H prime, right, is related to this, right?
Yeah.
But X is on an incline. H prime is a vertical. So you need to use the sign to convert that.
Yeah.
It's like a triangle that I have like this, right? This is the angle, 40 degrees. This is my delta X, and this is my H prime.
So we'll sign
So
H over X.
Yeah, that's why I have sine is H divided by the displacement. So I can relate this height here, right? There's a potential energy here that, you know, up to this point, right? So all potential energy is being converted into the compression, the elastic potential energy, right? This is elastic potential energy. Because when it's compressed, you know, it has energy to push back, right? It's being pushed down like that. If I remove the block, the spring is going back. Right? Stored energy on the spring. Is this okay?
Hold on.
This here, you know, is also important to see, because if the force is constant, right, the area is going to be F times X, right? But because the force is changing, you see here when I graph for different masses, different forces, you know, I have different distances, right? And the force, as I extend the spring, I have to apply more force to go further, right? I have the spring here. So the spring is here, like this. I apply one force, it goes this way. I apply more force, it goes this way. More, goes this way. More, now it's storing a lot of energy here, right? Unless if I let it go, it's gonna hit and hurt my finger. If I just go a little bit, that's nothing. A little more, it's getting stronger and stronger, right? It's bouncing back stronger and stronger. I don't want to go all the way and let it go, right? Because it can hurt my finger, right? Because more energy being stored on this spring,
So
right?
its force always going to be constant in that model, or?
Oh, this here, decay?
Yeah.
Decay depends on the spring, right? A weaker spring, K is going to be, you know,
But it's always going to be constant? Like what if, like,
Yeah, well, you know,
Like,
if,
what if your graph looks
good
different?
question, good
Would that
question.
be like
Yeah.
the tangent line?
Look.
If it gets used, then it's gonna,
You know, I can, what can happen, if I pull this too much, what do you think is gonna happen to this?
it's gonna stay.
Huh?
It's gonna be
It's
longer.
gonna run the spring, yeah. it's gonna-
Yeah, it's gonna deform, right?
Yeah.
So this is valid only for small displacements, right?
Mm,
If I start doing too much, then you're gonna damage, and then this law, this is called the Hooke's law, then this law, it doesn't work anymore. It's not valid anymore, okay?
I see.
Okay, so we stop here today, for today. And